students, in this video we will see some theorems. Let order pair y dy be a subspace of a metric space xd, then y is complete, implying y is closed. Y is closed. Okay. Let us see proof. See here, we have given that y dy be a subspace of a metric space xd. Then also we have given that y is closed, and we have to show that y is closed. Here our claim is y is closed. Okay. We prove that y contains all its limit points. So let x be a limit point of y. Let x be a limit point of y. Okay. Therefore, by definition of limit point, every open sphere, therefore, every open sphere centered on x contains points other than x of y. In particular, open sphere S1 by n of x, where n is positive integer, contains a point xn of y other than x. Therefore, distance between xn and x is strictly less than 1 by n, because here we have considered that open sphere S1 by n of x, where n is a positive integer which contains one point xn of y other than x. Therefore, we get d of xn comma x is strictly less than 1 by n. Therefore, sequence xn is a sequence in y such that xn converges to x in capital X. Here we get sequence xn is a sequence in y such that xn converges to x, and this x belongs to x. We know that every convergent sequence is a Cauchy sequence. we have already seen this theorem. Every convergent sequence is a Cauchy sequence. Therefore, this sequence Xn is a Cauchy sequence. Therefore, sequence Xn is a Cauchy sequence in X, in capital X, and hence in Y, because Y is a subset of capital X. Okay. But we have given that Y is complete. What is the definition of complete metric space? A metric space XD is said to be complete if every Cauchy sequence means if every Cauchy sequence is convergent sequence. So here sequence Xn is convergent in Y. Therefore, Xn tends to X as n tends to infinity, and this X belongs to Y. Hence, okay, and this X is nothing but limit point of Y. Hence, Y contains all its limit points, therefore Y is closed. Okay, see here, we have to prove that Y is closed. For this we will prove that Y contains all its limit points. So here we have considered that X be a limit point of Y. Here we use definition of limit point. We know that every open sphere centered on X contains point other than X of Y. So in particular we have considered that S1 by n of X be such an open sphere which contains a point Xn of Y other than X. Therefore, distance between Xn and X is strictly less than 1 by n. Therefore, sequence Xn is a sequence in Y such that which convergent in X. We know that every convergent sequence is a Cauchy sequence. Therefore, sequence Xn is a Cauchy sequence in X and hence in Y, because Y is a subset of X. But we have given that Y is a complete metric space. Therefore, in complete metric space, every Cauchy sequence is a convergent sequence. Therefore, sequence Xn is a convergent in Y. Therefore, Xn converges to X and X belongs to Y. Hence, Y contains all its limit points. Therefore, Y is closed. Let us take next theorem. Let order pair XD be a complete metric space. Let order pair XD be a complete metric space, and order pair YDY be a subspace of order pair XD, then Y is complete, then Y is closed, implies Y is complete. proof, see here. Here we have given that Xt be a complete metric space. Means every Cauchy sequence in X is a convergent sequence. Also we have given that Ydy be a subspace of metric space Xd. Then Y is closed implies Y is complete. Here our claim is Y is complete. Okay. When Y is complete, if every Cauchy sequence in Y is convergent, then Y is complete. We will show this. Okay. Let sequence Xn be a Cauchy sequence in capital X. Sorry, here we have to show that Y is complete. So here we will take sequence Xn be a Cauchy sequence in Y. Okay. Then sequence Xn is Cauchy in X, obviously, because Y is a subset of X. But in hypothesis we have given that Xd is a complete metric space. Xd is a complete metric space. And in complete metric space, every Cauchy sequence is convergent. So, sequence Xn is convergent. Sequence Xn is convergent sequence in capital X. Okay. Suppose limit n tends to infinity, Xn is equals to X, and this X is obviously belongs to capital X because sequence Xn is a convergent sequence in X. So limit of a sequence will go in capital X. Okay. Limit of the sequence, since limit of the sequence is also the limit point of limit of the sequence is also the limit point of range of the sequence. Limit of the sequence is also limit point of range of the sequence. Therefore, X is limit point of Y. Why this is? Because sequence Xn is a subset of Y and X is limit point of this sequence Xn, and sequence Xn is a subset of Y. Therefore, X is the limit point of Y. But in hypothesis we have given that Y is closed. Therefore, Y contains all its limit points. Therefore, Y contains all its limit points. Therefore, obviously, X is belongs to Y. Okay, and therefore, limit n tends to infinity, Xn is equal to X, and X is belongs to Y. Therefore, we get every, or say here, sequence Xn is convergent in Y. Here we have taken sequence Xn be a Cauchy sequence in Y, and we will get sequence Xn is convergent in Y. Therefore, Therefore, or we can say that every Cauchy sequence in Y is convergent. Therefore, Y is complete. Therefore, Y is complete. Okay. Here we have to prove that Y is complete. So here we have considered one sequence Xn be a Cauchy sequence in Y. Therefore, sequence Xn is Cauchy in X because Y is a subset of X. But we have given that Xt is a complete metric space, and in complete metric space every Cauchy sequence is convergent. Therefore, sequence Xn is a convergent sequence in X. Therefore, we get limit n tends to infinity Xn is equals to X, and this X is belongs to capital X because sequence Xn is convergent in X. Limit of the sequence is also limit point of the range of the sequence. Therefore, X is limit point of Y because sequence Xn is a subset of Y. But Y is closed, so Y contains all its limit points. Therefore, obviously X is belongs to Y. Therefore, limit n tends to infinity Xn is equals to n. This X is belongs to Y. Therefore, sequence Xn is convergent in Y. Therefore, every Cauchy sequence in Y is convergent. Therefore, Y is complete. Hence, proof of theorem is completed. Okay, let us see one corollary. Let order pair Xt be metric space. Let order pair Xd be metric space and Y is non-empty subset of X. Then order pair Xd is complete. If and only if Y is closed set in X. Okay, what is corollary? Xd be a metric space and Y is non-empty subset of X. Then order pair Xd is complete if and only if Y is closed set in X. Okay, let us see one example. Give an example of metric space Xd such that give an example of a metric space such that Y is closed subset of X as well as complete. Okay. We have to give an example of a metric space Xd such that Y is a closed subset of X which is which is complete. Okay. Let X is equals to Ru. R with respect to usual metric space. Okay. And Y is equals to closed interval 0, 1. Okay. Y is closed in RU. We know that very well. Closed interval 0, 1 is closed in RU and also complete in RU. Why this is? Because if you take xn is equals to 1 by n, this sequence or here sequence xn is equals to sequence 1 by n is Cauchy sequence in Y. Sequence xn is Cauchy sequence in Y as well as convergent in Y. Okay, this is the example of a metric space closed as well as complete. Okay, we will stop here. Thank you.